So let us first state this Minkowski's convex body theorem formally. Let R be a convex set in the Euclidean space Rn, which is symmetric about 0. Furthermore, we assume R is Lebesgue measurable with Lebesgue measure M of R. And sometimes we also call this the volume of the set R. Now if either M of R is strictly greater than 2 raised to the power n, where this n is the dimension of Rn, or M of R is greater or equal to 2 raised to the power n, and at the same time R is compact, then R contains an integer vector so denoted x with an arrow above. So formally this is in z raised to the power n with the origin removed. So this is a statement of the Minkowski's convex body theorem. Before we start the proof, let me remind you that those two conditions are kind of best possible. Do you see why? So consider the open cube denoted those vectors in Rn whose components has an absolute value strictly less than 1. In this situation, the measure of this guy can be easily seen to be equal to 2 raised to the power n. However, this cube is not compact, and you can also see from here that the only integer vector contained in the cube is just the origin, so it does not contain any non-zero integer vector. That justifies it that those conditions are best possible. Now let's give a proof. This proof is due to Waddell. The year is 1934. So let's first assume that the measure of R is strictly greater than 2 raised to the power n. M of R is bigger than 2 raised to the power n. Now for a positive integer, m greater or equal to 1, let R sub m to be the points x in R such that x can be written as a vector whose components all have the same denominator, m. So for the numerators, you may get L1 through L sub n, but in the denominators, you only get m. So this L sub I is in Z for any I. Now we make the following claim. We claim that if you consider limit as m go to infinity of the ratio, in the numerator you get the number of points in R sub m, and the denominator, it is the measure of R times m raised to the power n. And you take the limit of this guy as m go to infinity. You get 1. This says when m is very, very big, the number of points in R sub m will be asymptotically equal to the measure of R times m raised to the power n. Why is this so? I will let you think about it for a while, and I will tell the answer later. Let me first give you a hint. If you move this part to the numerator, what do you see? What is the limit of your numerator as m goes to infinity? The answer shouldn't be hard if you know the measure theory. So let's draw a picture. Suppose this is your convex and symmetric set. What we are doing here is that we are trying to divide this guy into small blocks. I talked about this idea in another video on the Gauss circle problem. So this picture stands for the case when our dimension is 2. And each cross in this grid is a point whose coordinates are some fractions with denominator m. The numerators are L1 and L2. Each small block is a square whose set length is precisely equal to 1 over n. Now, how do you count the number of those points in R? Namely, how do you count the number of points in R sub n? Instead of counting directly, what we are going to do is that we're going to put those squares centered at those points with set length m. So the set lengths of those squares are all equal to 1 over n. This is just one example. Actually, you're going to put those little squares everywhere, centered at those points that lie in R, and the denominators of each coordinate are all equal to m for each point. Now, in order to count the total number of R sub m, we're going to sum up the total area of those squares. And the cardinality of R sub m will be the total area of those squares divided by the area of each square. What you see in this picture is a case when the dimension is 2. In the dimension n case, there will be cubes, and the volume of each little cube will be 1 over m raised to power n. And the number of points in R sub m will be the sum of the volumes of those little cubes divided by the volume of each cube. So, as m go to infinity, the total volume of those little cubes will have the limit equal to the Lebesgue measure of this whole measurable subset. That is essentially due to how the Lebesgue measure is constructed in higher dimensions. So this claim will be nothing much more than just the definition of the Lebesgue measure in Rn. Okay, now let's move this part back to the denominator. This claim tells you that the cardinality of R sub m will be asymptotically equal to the measure of R times m raised to power n. But we assumed that m of R is greater than 2 raised to power n. So this part is greater than 2 raised to power n. So this claim tells you that for large m, the cardinality of Rm will be greater than 2m raised to power n, or just 2 raised to power n times m raised to power n. Now, by the pigeonhole principle, you know that there will be two distinct points denoted. The first one is acewise divided by m, and the second point is denoted b sub j divided by n divided by m. In Rn, satisfying the following congruence relation: a sub I is congruent to b sub I mod 2m, where I is from 1 through n. Do you see why? I'd like to think about it first. So in this application of the pigeonhole principle, what are your holes and what are your pigeons? Your holes are actually the congruence classes mod 2m multiplied by the integer n, because there will be n different indices here. The congruent classes mod 2m has 2m members. So your holes in this example will be for each I from n to n, the congruence classes. And there are 2m of them, because you are taking the modulo 2m. So the total number of hosts will be 2m raised to the power n. However, for large n, we know from the claim above that the cardinality of Rn is bigger than its power. So, by the pigeonhole principle, there exists two pigeons, which corresponds to two vectors or 2 points in here, that belong to the same hole, namely the corresponding coordinates are congruent mod 2m for each I through n, for each I equals 1 through n. Now, since this vector is in Rm, we have its negative is also in R sub n. So negative of this guy is also in R sub n. And now we consider linear combination of this guy with this, the first vector. We're going to consider the following linear combination. 1/2, 1/2. 1/2 plus 1/2 is equal to 1. So it follows from the fact that negative of second guy is in Rm, and this vector is in Rm, and the definition of the convexity that this guy is in R. And now let us denote this by x. This vector x is an integer vector because if you look at each component, because a sub I is congruent to b sub I mod 2m. So 1/2 of a sub I minus b sub I divided by m is an integer. So x is an integer vector. And x is actually a non-zero vector. That is because of our pigeonhole principle. So those 2 points are distinct by the pigeonhole principle. So we have found a non-zero integer vector that lives in R. This completes the proof for the case when R has the Lebesgue measure greater than 2 raised to the power n.